So let's start with the first law of thermodynamics for a closed system. So you could assume over here you have a fixed mass. So you have fluid inside this container, and this container could communicate with the surroundings because it could receive energy. So if the surroundings is cold, then the mass inside will eventually get colder. So, and the reverse is true. So if the surroundings is hot and the system over here is cold, then you have heat being transferred into the system. Also, if the system was a piston, for instance, then you could apply force by pushing the piston down, and in this case, you are compressing the fluid, and so it's gaining energy. And on the other hand, if it's actually pushing this, if the fluid itself is pushing against the system up, then what's happening is the fluid of the system is expanding, and so the fluid of the system is actually performing work against the surroundings. Also, let's say if you have a mixing tank of some sort and you have a shaft that's mixing the fluid, then you also have shaft work that's being applied into the system. So this is the equation if you look at it on a finite time interval. So the change of the total energy of the system over here is equal to the heat that is being added or removed from the system plus any work, expansion, contraction work the system does, plus any shaft work that's added to the system. So essentially, any change of the system's total energy must be a result of any of these three elements that change in the process. And the total energy of the system, in this case, it's just the fluid. So it essentially is composed of three things: internal energy of the fluid itself, the kinetic energy of the fluid, and the potential energy of the fluid. With the internal energy, it's just the sum of all the microscopic kinetic and microscopic potential energies of the molecules and atoms within the system itself. With the kinetic energy describes the macroscopic energy that the object possesses due to its motion. Potential energy describes the macroscopic energy stored within an object due to its position, arrangement, or configuration relative to a conservative field that is influencing it, such as the gravitational field. Now, in most heat transfer and thermodynamic applications, gravitational potential energy is the only field that is both significant and universally present. Other potential energies do exist, but they're negligible for typical fluids or not relevant to systems that we analyze. When other energy mechanisms are relevant, like chemical reactions, for instance, electric heating, we account for them in a separate term, usually in the energy generation term, and which you will see later. So this is the foundation that we need to understand for a closed system before we can move on to open systems. So again, in systems, you don't necessarily try to find the absolute energy of a system. We really care just about the changes of energy in a system. And the change of energy in this system will be due to either of these three components, because if you add heat to the system, then its total energy will rise and you're measuring that delta. Or if you're pressing against the piston, you're compressing the fluid, and so the pressure will rise and the total energy of the system will rise in proportion to how much energy is being added to it by the contraction work. And finally, you can also add energy to a system by applying shaft work. So the rotating impeller would provide energy to the system. Now, in most systems, if you don't have a mixer, then your equation reduces to this, which you might be familiar with because if you studied thermodynamics before, you might be very aware of this equation because it's one of the first things that students get to learn, where they say the change in the total energy of the system will be a result of any additional heat or heat that's being removed from the system, plus any expansion or contraction work of the fluid. Okay, so, before going to open systems, let's look at the internal energy term here. As we said, we can describe the energy of a fluid by three terms: its internal energy, its kinetic energy, and its potential energy. Let's understand what the internal energy term really is. So internal energy term, it includes sensible energy. So the temperature changes. So if a temperature of a fluid goes up, then its sensible energy starts going up. It also includes latent energy, and this relates to the intermolecular forces influencing phase change between solid, liquid, and vapor states. And so this means that, if a material changes from solid to liquid, that means, that material melts or it changes from liquid to vapor, so it evaporates, then its latent energy increases. And by the way, sensible energy here, which is related to temperature changes, this accounts for translational, rotational, and or vibrational motion of atoms and molecules. So obviously, if the temperature goes up, then you're going to have an increase in the translational, rotational, or vibrational motion of the atoms themselves. And so an increase in sensible energy. Chemical energy, this accounts for energy stored in chemical bonds between atoms. And you can have also nuclear energy included as part of the internal energy term, and this accounts for the binding forces in the nucleus. Now, for heat transfer purposes, in most heat transfer problems, the relevant terms we focus on are the thermal energy portion. So that means the sensible energy, which is U sense, plus latent energy portion, which is U latent over here. And so the changes in the others are mostly negligible. And so you could say that changes in the internal energy is comprised of the changes in the sensible heat and the changes in the latent heat when it comes to most of the heat transfer applications. And also, as I said, the chemical energy or nuclear energy, if there's any generation of these energies that are involved in the heat transfer applications we're looking at, then we're going to apply them in the energy balance with another term that we will see together. Okay, now let's look at an open system energy balance.